a very generous and kind invitation. It's my first time in Korea, and I like it very much. I'm very impressed by the beauty of the country and the richness of the culture. Okay, so today I would like to talk about Abel-Jacobi maps in or and motivic homotopy theory. But let me say right in advance that you don't need to be scared about a motivic homotopy theory if you don't know much about it. I could have also skipped it, but for some reason I thought like it's always nice to have a lot of fancy words in a title, but maybe that wasn't a good idea. Anyway, so let's start with a very simple example, and don't worry, like in a while I will try to switch gears a little bit. Let's start with an easy example. So take a very simple or fundamental geometric object, the circle, and so let's call it S. It's described by the equation x squared plus y squared equals 1, like in our xy plane. And now we could parameterize the points on the circle, for example, by measuring the arc length if we walk from some specifying point O, the origin, along the circle to the point P. And in doing so, well, in order to calculate this A, we need to evaluate a certain integral. And this integral looks like the integral from 0 to y of the function 1 divided by the square root of 1 minus t squared. Okay, so now when we do this, there are several things we should be careful with, or should consider. And so on the first hand, taking the square root of this function is not really a single valued function. So we have to make a choice. So either we take plus the square root or minus the square root if you want to like parameterize the points on the circle. And back in the days, like a long time ago, that led people, like even the masters of complex analysis, like Weierstrass, they thought, well, if we have this problem of not a single valued function, well, let's just look at multivariate functions. So let's allow a function to have not just one value, but like different branches, and then like consider these branches one at a time, and then study those functions and these integrals. But of course, you know, well, that's not what we're doing nowadays. We really look at functions that have a unique value. And well, Riemann told us that like the reason or the right way of doing this in this example is we should not look at like a variety of points in the target of our map, but rather we should look at a different type of domain. Like we should change the domain on which we define our function. And that's what we nowadays call Riemann surfaces. So in our example, what does it mean? So instead of looking at the real points just in our xy plane for the circle, we should really look at the complex points. Yeah? So we take our equation x squared plus y squared equals 1, and then we look at all the complex solutions. And then our function, we could write it then as, or we take an integral over the differential, which you write as dy divided by x. And then, so our integral now looks like, so instead of this function 1 divided by the square root, we write omega, and then take the integral from 0 to p. And well, in doing so, now we get a well-defined, like a holomorphic and bijective function, so a function with a unique value from the complex points, which I denote here by S of C, to the complex numbers divided by our modulo 2 pi over z. And this number 2 pi z is the period of the circle, and that's a like not very surprising name. We're all familiar with 2 pi as a period of a circle when we go around. Okay, so in some sense, so what we have gained now, we have a well-defined function, but there's still, well, some ambiguity is still involved, and that's captured by this period. Okay, so now let's move on to a slightly more complicated case. Let's look at the function, or the polynomial of degree 3. So before we looked at a polynomial of degree, or homogeneous polynomial of degree 2, and now let's look at one of degree 3. And let's try to evaluate or calculate an integral from 0 to some number t, 1 over the square root of this f of x. And now you all know that for such an integral, there's no simple or like canonical expression in order to calculate it. Yeah? But there's still something interesting we can say about this integral, and there's something that we can apply some of the knowledge that we just acquainted from Riemann, and let's see how far we can get with this. So in our modern terms, or like the way we just learned how to formulate the problem, we look at the following situation. So we write an equation y squared equal f of x and call this E. And then with this equation we can just rewrite, so remember y squared is equal to f of x, and then 1 divided by the square root of f of x now looks like dx divided by y. And then we call this omega. And once again we look at all the complex solutions of this equation y squared equal f of x. And then, well, our integral now, instead of writing the function, we just write here omega, so just a shortened notation. And we write p for some solution on this, or some point on these complex points of or complex solution of our equation. And now here's something very remarkable that Euler already found out about these integrals. And that was actually like how they got their name. So he found out well, even though we don't have a simple expression for evaluating the integral, there's an expression or a rational function that tells us if we throw in a point p or some value t, if you remember the initial integral, and some other value t prime, then there's a rational function that expresses the thing that we have to plug in here in order to make this equation true. Yeah, and like in modern terms, of course, now you know this group law, this p plus q, that's the group structure on what we now call an elliptic curve given by this equation. Yeah? Okay, but it's like all this information is hidden in this, was contained in this equation. Okay, so now let's try to calculate this integral. So now we write I of p instead of I of t for this integral over omega. And now, so in order to calculate this integral, we have to choose a path where we go from, let's say, some specifying point O, which we think of as the origin or like the neutral element on our elliptic curve. And then we want to evaluate an integral walking along some path to p. And it turns out that this integral, well, it depends on the path that we choose, but only up to homotopy. Right? So our integral depends on a then so-called homotopy class of a path. Okay. So what this means is that really this function, when I start with a point and then send it to the complex number which is given by this integral, then it's really a function on the so-called universal cover of this of E of c. So remember, E of c was all the complex solutions of our equation. And universal cover, well, it just means that I think of the space of all possible paths. Yeah, so I just collect all the paths that I have on my geometric objects, and I just make it into a new space. And then this function of taking the integral defines the function here. And the inside of Euler, remember this formula for integral to p, integral to q is integral to p plus q, tells us that this map here is actually a group homomorphism. Okay, but still we would like to make it into a function or a map on this E of c. So how can we do this? So I said in order to calculate an integral we have to make a choice of a homotopy class of a path. So let's try to make this canonical, try to find out what kind of ambiguities there are. So let's choose two closed loops, so paths that start at a point and then they end again at the same point. And well, now we use our modern knowledge about how the topological or the shape of these complex solutions look like, and we know that we only need to choose two different loops, and they will generate all possible homotopy classes of loops. So we choose a gamma 1 and a gamma 2 loops on our curve. And now remember, omega was this dy divided by x, so it's some differential. Now we can evaluate this omega along the loop gamma 1 and gamma 2, and then we get two complex numbers, omega 1 and omega 2. And just like in the case for a circle, we call these numbers the periods of our elliptic curve, or of our equation E, let's say. Okay, and now this map sending a point P on our curve to this integral becomes a well-defined map from these complex solutions to the quotient of the complex numbers modulo the lattice, which is formed by, so z stands here for the integers, so z times this complex number omega 1 plus z times omega 2. And this defines the lattice in the complex numbers. And if we take this quotient, then we actually get not just a well-defined homomorphism, but it's actually an isomorphism. Yeah? And we call this quotient here on the right-hand side the Jacobian of the equation E, or of the elliptic curve. Okay. So the nice thing about this is that, well, here we just have point on some mysterious curve. On this side, well, after we calculate, if we are able to calculate these two numbers, then we just have a very nice complex torus, just a complex numbers modulo some lattice. So we can study that and understand that. Okay, so now let's see if we can generalize this. So before I started with this curve of genus 1, so this polynomial of degree 3. Now we can also do this for more general cases. So we can do this for a complex curve of genus G. And then what you do is, well, now we don't have just one differential, but genus G means we have like several differentials, exactly G many, in order to like span the space of all possible differentials. And then if we take 2 points PQ on our curve now, well, before we picked the point 0, now we allow any point Q, and then we can take this pair of Q's of points and then take the integral from Q to P over omega 1 and so on. And now this map, well, we can now describe this map as a map from the divisors of degree 0 modulo some equivalence relation now to another quotient of the G-fold product of the complex numbers modulo some lattice, which is again given by like the periods in a similar way associated to our curve S. And then this quotient is called the Jacobian of the curve. And the Abel-Jacobi theorem tells us that this map is still an isomorphism. So even for these more general curves of genus G, we can describe, so the divisors just means, so we always, of degree 0 just means we take always like pairs of points on our curve. Yeah, so we can study these points on our geometric object, which we may not understand very well, in terms of this rather simple quotient. Okay, so now this map is actually the first instance of the Abel-Jacobi map, and also the map that we looked at before. So taking this integral over some differential is the examples or instances of the Abel-Jacobi map. Okay, and we see here now in this example that it might be very useful. It looks very useful for studying geometric objects. Okay, now let's look at. Can we do this also then in higher dimensions? So before we only looked at a curve, yeah. And now what happens if we start with a smooth projective complex variety of some higher dimension? So once again, a complex algebraic variety is just given by, you take like a list of, so before we had only one polynomial, now we take a list, like a list of polynomials, and then we look at the complex solution, so in several variables, and we look at the complex solution of these polynomials. And then look at it, consider it as a geometric object, and we call it a variety. Okay, so now we look at, so before we looked at points on this curve. So now we have higher dimension, and of course, like a point on a curve, so a point is something 0-dimensional, a curve is something 1-dimensional. So the codimension, so the difference between these two dimensions is 1. So now we generalize this to higher dimensions, and so we allow codimension p instead of just codimension 1. Okay, and then we take a subvariety now, so some like nice subset of our variety x. Okay, and now we assume that this subvariety z. Okay, now here z is, because it's so common to use the letter z, so it's not the integers, but here in this case subvariety. I apologize for these ambiguities, because here in this case it's the integers. I have to work on the fonts that I'm using. Okay, so now before we had always a pair of points, and we could connect them by a path. Yeah, there was like the assumption we made to to be able to calculate these integrals. Now the analogy for this is we have the subvariety, and now we think of it, we consider it as the boundary of some little bit higher dimensional like differentiable chain, or like let's say there's some other like manifold or geometric object in one dimension higher, and the z is just the boundary of that thing. And that's exactly like corresponds to the assumption that we take points which are connected by a path or by a line, and then the 2 points in the end are the boundaries of that line. Yeah, so that's the exact analogous situation. And now if we take some differential form of it's of degree 2n minus 2p plus 1, then we can define a map by sending this omega to the integral of this differential form evaluated on this differentiable chain gamma. And this defines a map from, so here I write a to the 2n minus 2p plus 1 for the smooth forms on this x of degree 2n p minus 1. And then we get, so if we evaluate this integral, we get a complex number. Okay, so now there are two things that we would like this map to satisfy. On the one hand, we would like it to descend to a map on cohomology. So you remember, if you think of the RAM cohomology, then you know that you can represent any cohomology class by a closed differential form. And so we just said like, well, we just define a map on smooth forms using this integral. Now we want this to become a map on cohomology, and therefore we need to show that it vanishes on exact forms. Yeah. So we need to check that. And on the other hand, well, we wanted to be a map that is defined just by the z, yeah, so our subvariety. And so far we defined this integral using this gamma, and we made a choice in picking the gamma. There might be other gammas that have the same boundary as that, and we make to check how this depends on our choice. Okay, so now for the first thing, let's assume that omega prime is a form such that the differential of omega prime is omega. So in other words, omega is an exact form. So then Stokes' formula tells us that if we evaluate omega on gamma, so the integral that we looked at on the previous slide, is the same as omega prime evaluated on z, yeah, on our z that we had before. Okay, so here's again Stokes' formula. So what does it tell us? Well, it tells us that if we pick just the right type of form, omega, then we actually get a well-defined map on cohomology, because if omega is a form of a certain like type, you remember if you have a complex manifold or smooth complex variety, then you can describe the holomorphic forms, or take a resolution of the holomorphic forms by smooth forms, and they have like a dz part and d bar z part, and you can like filter them using like how many dz's and how many dz bars are there. And then you call them like they're of certain type, and then we notice that if it's a form of a type p prime and then 2n minus p plus 1 minus p prime, when p prime is bigger or equal than n minus p plus 1, then because that was an algebraic variety, this integral always vanishes. Yeah? So now we learn that we get a well-defined map sending z to this functional of evaluating some form on this boundary gamma, if we restrict our cohomology forms to those which lie in the filtration step n minus p plus 1 on the complex cohomology. Yeah, so F denotes here the Hodge filtration of complex cohomology. And then so this here denotes the dual, so we get a map that sends something in here to a complex number. And now the ambiguity of choosing the gamma is something such that the boundary of gamma is z. Like we can't get rid of it, but we can get rid of it if we consider this here by modulo the quotient given by homology, or this homology group. That corresponds exactly to the situation we had before for the Jacobian of a curve where we had to mod out by some lattice which was given by the periods. And here I write ZP homologous or H for now I collect all the codimension P subvarieties, and H means they are the boundary of something else. So in other words, they're homologous, or so they vanish in their image vanishes in cohomology or in homology, if you, whatever you like. And now this mu is again, or it's like the higher dimensional version of the Abel-Jacobi map. And we call this quotient here now, as just an analogy to the case of curves, we call it Griffith's intermediate Jacobian. Yeah, so it's a generalization of the Jacobian for higher dimensions. Okay, so now, well, before we had the theorem of Abel-Jacobi, and so ideally we would like this map here, maybe modulo some equivalence relation, to be an isomorphism. Yeah? Unfortunately, it's not in higher dimension, or in general in higher dimension. But there's something, there's still something very interesting about this torus and about this map. And it's very useful. And let's try to find out what it's useful for, and in order to do so, let's put it in a bigger picture, all these maps. Okay, so we start again with the smooth projective complex variety of some dimension. And now, well, as I said, now we look again at the codimension P subvarieties in my X. And now, so I take the free abelian group on them, and then I model out some equivalence relation, which is here called, which is rational equivalence. And it's just to make things a little bit nicer. Just like for the divisors on the curves, we also had to consider some equivalence relation. Just the thing that the Abel-Jacobi map and all the other maps that we look at factor over this relation anyway. Okay, so but this thing here collects the information of all the subvarieties in X of codimension P. So we just defined the torus, this Griffith's intermediate Jacobian. But there are like several other interesting groups that we can are associated to the CHP of X, which is also called the Chow group of X. Because there's a classical cycle map for Chow groups, and that associates to any codimension P subvariety a class in the singular cohomology of the underlying topological space. And it turns out that this cycle map actually lands in the so-called Hodge classes in the cohomology. It's just a certain type of, or nice type of cohomology classes. And this map works like this. So we start again with a close, let's say, irreducible subvariety, and then we send it to the fundamental cohomology class. And well, if that was not a smooth variety itself, then we may have to take a smooth resolution to make it nicer. Well, we just take the associated fundamental class of the subspace. Okay, and well, we just learned that on the kernel of this map, so there was exactly the situation. So if the set goes to 0 in cohomology, that exactly means it is the boundary of some higher dimensional chain or cochain. So on the kernel of that map, we just defined this Abel-Jacobi map that we described using integrals over differential forms over some chains. But now these two maps and these two groups, they are actually connected and by something that sees both of these maps, and that's the so-called Deligne cohomology of my smooth project of my variety X. And the Deligne cohomology actually sits in a like short exact sequence, so the Jacobian is injected into the Deligne cohomology, and the Hodge classes here, these cohomology classes, are a quotient of Deligne cohomology. So in some sense, Deligne cohomology sees both of these worlds, both the cycle map and the Jacobi map, because of course, well, it's useful because we also have then a separate map from the Chow groups to Deligne cohomology. And now, what is the Abel-Jacobi map good for? Well, Griffith showed that, well, there are a lot of reasons, but let me just state like one reason. So Griffith showed that there are examples of varieties, and they can be as simple as just a hypersurface in projective force space, and then you can find like different lines on this hypersurface, and then he showed that the image of the difference of these two lines under the Abel-Jacobi map so the L minus L prime is like goes to 0 in cohomology, so we can like the Abel-Jacobi map is defined. And then he showed that that's a non-torsion element in J3 of X. And the nice thing about this is, so he showed with this example that, so it would be very hard to show that something is like non-torsion or has like certain properties here, but it was much easier to show that in this Jacobian. And therefore we also showed that there are cycles which are homologous to 0, but not algebraically equivalent to 0, which are non-torsion. And therefore like this Griffith group that we now call the Griffith group can be infinite. So in order to find something out about the kernel of the classical cycle map, which is a very natural thing to look at this algebraic subvariety and send it to some like cohomology class, which you can understand by all kinds of topological methods, is a very useful thing. Okay, so now why am I telling you this classical old story? Because there's actually another very interesting map for smooth complex varieties. And that's the map from algebraic cobordism, which we denote by omega star of X, to the complex cobordism of the underlying topological space. And let me quickly remind you of how these two things are defined. So first of all, let's start with the topological side. And like in general, it's not so important if you have never seen either of those guys. Just think of them as natural generalizations of the situation where we look just at subvariety of our X. And it's like a natural question, if you want to study the geometry of some object, well, you try to understand all the possible geometric subobjects in that X. Okay, so but if you want to know how this mu is defined, so it's generated by, you take the complex points of Max, so it's just a topological space, even a complex manifold, and you look at all maps from some manifold, or it should be more precisely should be a weakly complex manifold, but that's not so important. So we take all kinds of like the smooth manifolds, and then just take continuous or proper maps to that space, and that's like collect them. You order them by the codimension, and then there's some equivalence relation where you say that like the fiber of some map 0 and 1, they are equivalent if you find some bigger one-dimensional higher smooth manifold W, and then the restriction onto 0 is something smooth, another smooth manifold, and the restriction to 1 is another smooth manifold. And then if you have this bigger W, then you call these two things equivalent. Or in other words, they're cobordant, if you're familiar with this term. So in other words, you could also think of it as you want to call two manifolds which are living over with maps over X to be cobordant if there's a bigger manifold such that these two manifolds are the boundaries of that. So it's a very geometric idea. Okay, so this guy is a very useful and actually universal cohomology theory. And omega stars is the algebraic version or analog of this, and let's see how this guy is defined, or remind you how this is defined. So omega p of X is generated by projective morphisms. Now we're in the algebraic world, so we just look at a projective morphism of algebraic varieties of some codimension, and then where Y is smooth, and now modulo some relation. And now in the beginning, so algebraic cobordism was developed by Levine and Morel, and they had and the initial construction was a little bit more elaborate and less direct, or not as geometric as in topological case. But then Levine and Pandoripande showed that, or found out what is the correct geometric relation that we need to mod out. That's a so-called double point relation on algebraic cobordism. And what does that mean? So once again, we say that two fibers of some map, they are equivalent if we have some projective morphism pi from some bigger variety y prime to x times the projective line. So instead of the real line, the real numbers, we look at the projective line. And then we require that one of the fibers must be smooth, and for the other fiber, over infinity or over 1 if you want, we allow it to be like, we have two smooth things, but they are allowed to intersect once, or like intersect transversely at some point. Yeah? So the fiber over infinity does not have to be smooth anymore. And the point was, you could also think of a relation where you just do the same thing as in topology. You require that the two fibers over 0 and infinity are both smooth. But it turned out that it was easy to see that you don't get enough relations. Yeah? So there was more needed to do that. Okay, but the thing that you should keep in mind is that both in these cases, in the algebraic case, you look at, so omega is generated by all the like algebraic varieties mapped to X, and in the topological case, you took like just manifolds mapped to X. So very similar construction.
Excuse me, what is the relation exactly? So the fiber over 0 is A plus B, or?
No, the fiber over 0 is smooth,
yeah.
And the fiber over infinity has two components. Well, it's like two smooth components, but they are allowed to intersect transversely in D. It's also allowed that there's just one component. So it's also allowed that it's smooth. But if they intersect in some point, then at that point it's not smooth anymore. So yeah.
I'm still. Can you go back so I can see?
Yeah. Yeah, for sure. I have to always start at the beginning of the slide. So I have two components. Both components individually are smooth, but they're allowed to intersect in some point. So I have one component and one other component. Yeah.
But then which maps are equivalent in the?
So I get an induced map. Oh yeah, maybe so there was a short form. I apologize. So you get an induced map from the fiber over 0 to X and a map, so the fiber over infinity to X. If you take the inclusion from X at 0 and at infinity, you take the pullback and then, okay, then you get a relation. Okay, so let's think a little bit about this as relation. So first of all, how is then this map defined? Well, we just saw the structure of the generators is very similar. So here we took these projective maps from some smooth variety Y to X, and now we can just send it to the corresponding map of complex points here, so just underlying topological map. So it's very natural way of defining this map. And then, well, this you have to show that this map is actually well defined also modulo the equivalence relation. And well, what this tells us is, so first of all, we can also look at, so sending some y is sent to 0 under this map defines now a new equivalence relation. And well, so to define omega, we had the double point relation. That this map is well defined tells us that any of these double point relation is actually sent to this topological cobordism relation that I described before. Okay, so in terms of like comparing these occurrence relation, we could say that the double point relation is finer than topological cobordism relation. So in other words, we can like the relations. So the relations on the left hand side are contained in the right hand side. But now it turns out that there's another very interesting equivalence relation in between, and that's so-called algebraic equivalence, and that has been developed and studied by Krishna and Professor Park. And that's well, that sits in between these two guys, and that plays exactly the role that algebraic equivalence plays for Chow groups. And so this one would play the role for rational equivalence and Chow group. If you're familiar with this one would be correspond to algebraic equivalence, and then this one to homological equivalence. Yeah. So an algebraic equivalence sits inside these three relations. Okay, so now our goal is, or my goal is today to say a little bit more about this, well, whatever I can say about this map. Okay, so if you think of a map, well, what can we describe? Well, we can think of like the image and the kernel of the map, for example, yeah, to say something. So let's start with the image. So there's something obvious we can say about the image, and that is, well, there's also a canonical map from omega star to these Chow groups that we looked at before. And we also had the classical cycle map, which again went from the Chow groups to Hodge class, which were like just some special classes contained in the singular cohomology of X. And now there's also a canonical map from cobordism to cohomology. And now, while this map, just by universality, so this algebraic cobordism is like a kind of a universal cohomology theory for algebraic varieties in a certain sense. So this tells us, this universality tells us that this diagram commutes. And that tells us, well, if we go this way and then land in the subgroup of Hodge classes in cohomology, then if we go that way, we also have to land in this one. So the image of phi must lie in the subgroup of elements that actually map to Hodge classes. So in some sense, that tells us there's some, whatever it is, Hodge theoretic restriction for the image of phi. And we will try to find out a little bit more about that in a minute. Okay, and now what about the kernel of the map? Well, Griffith's theorem, and also the fact that we had this, that algebraic occurrence sits in between double point relation and topological cobordism relation, suggests that phi should not be injective. And it's not. But how can we detect this? And we learned from Chow groups that one way of detecting something in the kernel of that map, the map from the Chow groups, was to use the Abel-Jacobi map. Yeah? There was a way of detecting elements in the kernel of the cycle map. So the question is, like, is there an Abel-Jacobi invariant which detects element in the kernel of phi? And actually there is. And how do we come up with the right construction for this map? So remember our fundamental diagram that told us, like, that combined all the different stories was this diagram where we had the Chow groups, and then here the Abel-Jacobi map, the classical cycle map, and this was the Deligne cohomology. So now in a joint work with Michael Hopkins, I tried to generalize this picture where we replace the Chow groups by this algebraic cobordism. And so the goal for the next 20 minutes is define new invariants for algebraic cobordism instead of the Chow groups, which combine now some sense Hodge theoretical information, because that seemed to play obviously a role also for the image, and also topological information now of complex cobordism, because the natural map that we want to study is from algebraic cobordism to complex cobordism. Okay, so let's see how we can do this. So we will do this by actually, we're going to generalize now what the Deligne cohomology, the role of the Deligne cohomology here for this diagram. And then we will see that the other map, the Abel-Jacobi invariant, will just come up naturally and automatically. Okay, so let me just very briefly recall how the Deligne cohomology is defined. And like for another 5 minutes, will be very technical. If you're not interested in the concrete construction, you can sleep for 5 minutes and then wake up and start to listen again. And then I will tell more about the consequences of our construction. But it's actually very natural and like easy to understand how we come up with this thing. If you accept how we define how the Deligne cohomology is defined. So the Deligne cohomology is defined as some complex of sheaves, which you call like ZD of some given integer or natural number p. And it can be defined on any complex manifold, or if you want, just think of a smooth complex variety. Okay, and it's given by a homotopy Cartesian square of sheaves of complexes. So just, if you don't know what homotopy Cartesian means, just think of a Cartesian square of sheaves of complexes, or if you want, just of complexes. And where we start with the locally constant sheaf Z, just as a complex considered in just concentrated in 1 degree. And then we have a natural map to smooth forms on X. And then we can filter these forms as before by so we look at the number of DZs and DZ bars in the differential, that's the differentials, and then there's a natural inclusion into all forms. And then we take the homotopy pullback, or if you want, just the pullback of that diagram as sheaves of complexes. And that's the Deligne complex. And then you define the Deligne cohomology as the hypercohomology, or just, if you want, just cohomology of that complex. Okay. So now we would like to generalize this. How do we do this? So here's our diagram we looked at. So first of all, I said we want to combine information from Hodge theory or differential forms and topological complex cobordism. So first of all, we have to throw it into some joint world where all these things can be compared or mixed up together. And so the first step is, instead of looking at sheaves, we look at pre-sheaves. That's just a technical thing. We don't want to get stuck on just one specific X. We don't want to have the freedom to look at all possible varieties. And then instead of complexes, we look at spectra on the side of complex manifolds. Spectra is a term from topology. If you're not familiar with it, just think of nice topological spaces, or if you want, just think of them still as complexes. Okay, so now there's a functor which sends every such complex to a spectrum, and that's the so-called Eilenberg-MacLane functor H. So all we do is now we just throw our diagram in a new world where we combine it with something else. And if we now in this new world take the homotopy pullback, then we still get the right thing. So this new guy we just defined still represents the lean cohomology in now the homotopy category of pre-sheaves or spectra. It's not so important what that actually means. The point is that we just went to a new world, and in this new world we could still get the same invariance that we had before. But now the nice thing is, now on pre-sheaves or spectra we can easily generalize our construction. And this goes by, so the contribution of this Z here, or the Eilenberg-MacLane spectrum of Z, is related to that, or plays the role of, that comes from singular cohomology in the Deligne cohomology. Now we want to replace singular cohomology by this complex cobordism. So now we just replace this guy here by complex cobordism. So now, because mu, well, it's just the theory mu is also represented by a spectrum. So there's a natural candidate for that thing. Okay, now we also need to modify a little bit the other corner. So instead of just differential forms, we look at forms with coefficients in the complexified coefficient ring of this mu, just some nice ring. So we just have to enlarge a little bit our coefficients. There's nothing fancy going on. We do the same thing on this corner, and then we have to just, for technical reasons, a little bit more careful to make this Hodge filtration somehow compatible with the grading on the coefficient. But that's not very important. And now we can form a new homotopy pullback diagram and define the thing that we get on the left-hand corner here as our new Deligne cobordism spectrum, or however you want to call it. Okay, so now here's still our diagram. Now just to complete the story, now you can define these cohomology groups by just being the thing that is represented by this spectrum in this world of the homotopy category of spectra. Okay, just the usual thing you would expect from how you define some cohomology theory. Okay, so now just by defining this guy as a homotopy pullback, there are natural long exact sequences, but instead of which relate the cobordism groups, and here these the coefficient groups of which is just singular cohomology and then Hodge filtered cohomology together. Instead of writing down all these long exact sequences, I just tell you what the very interesting short exact sequences are and how they fit into our picture. Okay, so we had before, in the Deligne cohomology case, we had this short exact sequence. And now, with our new construction, we get a new short exact sequence, which is a generalization of this one. So we have natural maps now from, here was the thing we just defined, it maps to Deligne cohomology. Here are these, well, I call them now mu Hodge classes, but they're still just the thing that it's a subgroup of mu2p of x of the classes that are mapped to Hodge classes in cohomology. But here the kernel is now a new thing, which I think of as a generalized Jacobian. It's still a complex torus, and it generalizes the role of the classical Griffiths intermediate Jacobian to cobordism. And as a real Lie group, this is isomorphic to mu2p minus 1 of x tensor R mod z. Okay, so now, well, there's also, well, we can, like for the experts, like improve this version a little bit using ideas of Beilinson, and then like to remedy some defects that if you have not a compact or non-projective variety, then you get actually a motivic ring spectrum, you get a projective bundle formula, and then this bundle formula gives us a natural map, now again from algebraic cobordism to this new guy, if we take the direct sum over 2pp. And it's actually a ring homomorphism. So we also have this map in the middle of our diagram. So to summarize this thing, so here we have again our short exact sequence. Here we have the map phi that we looked at before, just given by sending it to the complex points. Here was now this new map, which is given by the push forward. And now automatically we've produced define on the kernel of this map, because this is a short exact sequence. On the kernel of this map we have a new map, which is the generalization of the Abel-Jacobi map. So it just pops out very naturally after we defined this this thing here. Okay, so now let's wrap up our information. So what can we say now about the image of phi and about the kernel? So let's think again about the image. So we already know it's a map that goes into these mu Hodge classes, which is just a certain subgroup. Well, of course, if you think of the Hodge conjecture, you would like it to be surjective. Yeah? So it would be nice if you can get every algebraic, if for every topological map here, you get an algebraic map on the left-hand side. But, well, you can expect, this is probably not true just as for the integral version of the Hodge conjecture. But it's actually, it is, at least for me, it's much harder to see why it's not true, and I don't know, I still don't know an example of how to come up with, but probably some smarter person has an example already in his head. Because there's some problem for me in order to come up with a counterexample, and that is related to how the Atiyah and Hirzebruch, and then later Tutaru, he generalized this idea, came up with counterexamples to the classical integral Hodge conjecture. And that went as follows. So if we can reinterpret this now in our terms as follows. So we start with our map. Then we can look at, we get an induced map if we take the tensor product of both sides with the integers over the Lazare ring, so which is the coefficient ring on both sides. Just some nice ring. Or like important ring for formal group laws. We get an induced map, and then we also have this canonical map to the Chow groups, and it turns out that this canonical map from omega x like factors to this quotient. We still have the classical cycle map here on that side, and we also have the canonical map from omega 2 star x, again now factors to this quotient to cohomology. And now on the, well, and we have seen that if we look at starting from here, then the image actually goes into these Hodge classes. And now on the algebraic side, we know that this map here is actually an isomorphism. So the Chow groups are just given by this tensor product. And that means that we get an induced map, so we can like factor this map to the Hodge classes over this quotient, because we have this map. But now in the topological side, this map here, the corresponding map to this one, is in general not an isomorphism. And that causes, like, you could see this as a problem or as a dilemma. But on the other hand, it also gives you a lot of like powerful techniques and methods to prove something about this cycle map. Because Atiyah and Hirzebruch, they use this fact that this map, like the classic cycle map, factors to this quotient, and this is not an isomorphism, to show that there are Hodge classes in here which cannot lie in the image of that map. And the reason is exactly that there have to be, if something wants to be in the image of the cycle map, it has to be in the image of this map. But now if we wanted to copy this argument for this situation, we don't have a corresponding thing here on the top. Yeah, we don't get an automatic topological obstruction for something in the image. Yeah, so we need a new idea for that. Okay, unfortunately I don't yet have the new idea, but I wanted to tell you like how this works. Okay, so well, as I said, this argument doesn't work for phi. Now what can we say about the kernel, so about this Abel-Jacobi map? Very briefly, let me summarize. Well, just for to give you an idea of how it is, it's a little bit technical, well, by the nature of the things. But one way of defining it is, and it looks actually like very similar to the construction or the classical construction that I described in the beginning. So we can describe every element in this cobordism ring as a sum of where we take, oh sorry, the Zi was, so the tilde should be here, so Zi is a subvariety of some codimension, and then if I take a resolution of singularities and then I take the classes in here, then I can actually allow like elements in the Lazare ring as coefficients, and I can describe any alpha as such a sum. That's Ross degree formula, which was proven by Levine and Morel. And now if you assume that alpha lies in the kernel of phi, then there are like, we can again produce some differentiable chains, Ci, in like for every I from like 1 to k. And then with some, in some way we can interpret that if you take the boundary of the sum of these guys in this group here now, then that's exactly the image of phi also in this group. But I put this in like quotation marks because you have to interpret what this means and a little bit what the boundary means and so on. But the idea now is now the same as for the classical Abel-Jacobi map. So now if we take modulo the lattice now, instead of homology we take the bordism groups in a certain degree, then on the kernel of the map phi, we have again a map where we send alpha to the sum of these functionals over some chains with now coefficients in the Lazare ring, and then modulo these bordism groups, we get a well-defined map. Okay, so it's a very similar description. Now, what can we say about this map? Well, we can actually produce examples where which show that this Abel-Jacobi map is actually able to detect at least some interesting cobordism classes. And we can produce an alpha, or like different ways of producing alpha such that, well, they're mapped to 0 to Chagu. You could wonder, well, if we produce something that already also lives in the Char group, then you could say, well, I could have seen it already with the classical Abel-Jacobi invariant, and which also is mapped to 0 in cobordism, so it lies in the kernel of our map phi, but which is non-zero in this thing. And well, what does being non-zero here means? That means exactly that if you think of how our Abel-Jacobi map was defined, it means exactly that alpha is detected by the new Abel-Jacobi map. So it's a non-zero element in this generalized Jacobian. Okay, so the hope is that this new generalized Abel-Jacobi map will be useful, or is useful for understanding better the structure of algebraic cobordism classes. But so far, like, these types of examples are the only thing I have. But I'm optimistic that it will produce more interesting examples in the future. And that's all I have to say. Thank you.